Okay, we're in Physical Chemistry, Chapter 18, Section 8 now. We're going to talk about a particle in a one-dimensional box. This is a very crude, primitive model. Now let's say we have an x position here on the horizontal axis and potential energy here on the vertical axis. So we have three regions, region 1, 2, and 3. So we have this mass in region 2. Now it can't get over here into region 1 because it's blocked by something with infinite potential energy. And likewise, it can get as far as position A. So it can't get over to region 3, same reason. It's blocked by something with infinite potential energy. So because of these being blocked by the two locations with infinite potential energy, or we'll say if the mass was here, it would have infinite potential energy, then the mass is trapped inside of this box here and positioned from 0 to A. That's lowercase a. So we're going to say that the potential energy is 0 when it's inside the box, but it's infinite outside the box. So it can't be out in region 1 or 3 because they would have infinite potential energy out there. And like I said, 1, 2, and 3 are regions. So like I said, we write the potential energy is 0 for x. 0 is less than or equal to x is less than or equal to a. So x is the current position of the particle. X is position of particle. And then we say the potential energy is infinite for x is less than 0 or x is greater than a. So this particle is confined within the box. Now here's a formula. We're going to write minus h bar squared divided by 2m times the second derivative of psi with respect to x plus the chemical potential energy times psi equals E times psi. So this is only if you're thinking in one dimension here. And remember, psi is a function of x, so that's why we write psi is psi of x only. So this is time independent because psi is not dependent on time, just x. So we define psi in region 1 is equal to 0. Psi in region 3 is equal to 0. Since psi, we say, is well behaved. Now, we know that the probability, the absolute value of psi in region 1 squared is equal to 0. And we know that absolute value of psi in region, psi in region 3 squared is equal to 0. So we say the probability of it being in region 1 is 0, and the probability of it being in region 3 is equal to 0. So for region 2, we get psi is not equal to 0, but chemical potential potential energy is equal to 0. So we're going to start out with minus h bar squared over 2m times the second derivative of psi with respect to x is equal to energy times psi. We'll call that equation 1 for now. Now we get the second derivative of psi with respect to x is equal to minus 2 times the mass times energy divided by h bar squared times psi. And this is equation 1 just written in a different form. Now that is a second order differential equation that we need to solve. Now we're going to have a trial function here to see what happens. We're going to say that psi is equal to a times sine rx, so that's lowercase r times x, plus b times cosine sx. So we're going to say that capital A, capital B, lowercase r, and s, these are all constants. So a and b, capital A obviously, b, are integration constants. Now we're going to have the derivative of psi with respect to x then would be ar cosine rx minus b s cosine x. So the second derivative of psi with respect to x is going to be minus ar squared sine rx minus b s squared cosine sx. We'll call that equation 2. Now we're going to substitute equation 2 into equation 1. So we get minus ar squared sine rx minus b s squared cosine sx equals minus 2m e over h bar squared times psi. We'll call it equation 3 for now. Now, let's say that S and R are both the same. And we're going to say that that's going to be equal to the square root of 2 times m times e divided by h bar. So that means S squared is equal to R squared is equal to 2me over h bar squared. Then we get minus a times 2me over h bar squared times sine rx minus b times 2me over h bar squared times cosine of sx is equal to minus 2me over h bar squared times psi. Now we're going to divide everything by 2me over h bar squared because it's everywhere. So we just end up with psi is equal to a sine this whole quantity here. The square root of 2me over h bar times x plus b times cosine of the square root of 2me over h bar x. And this is only valid for 0 is less than or equal to x is less than or equal to a. Now we call this the general solution. If you're taking differential equations, you know what that means. But what that means for this class is that we need to find a more specific solution called the particular solution. So now we need to find a and b by imposing what we call boundary conditions. So we need to make sure that when x is equal to 0, psi is equal to 0, because that's one of our boundaries, the left boundary. And when x is equal to a, and psi is equal to 0, that's because that's our other boundary, the other edge of the box, as you would. So for x is equal to 0, we just say 0 is equal to a sine 0 plus b cosine 0. So b has got to be equal to 0. And for x is equal to a, we get 0 equals sine 2m, the square root of 2me over h bar times a plus 0, since b is equal to 0. So we substituted that in. So that means that the square root of 2me over h bar times a has got to be equal to plus or minus pi times any integer, 0, 1, 2, 3, etc. So now we get 2me, the square root of 2me over h bar is equal to plus or minus n over a times pi. Okay, we'll call this equation 4. This is a different form. Oops. Get to the next page, ready? So now we get psi is equal to a sine plus or minus n pi x over a is equal to plus or minus a sine n pi x over a. Now the plus and minus, they'll give the same solution, so we can just be lazy and drop that off. So we're going to say psi is equal to a sine of this whole quantity n times pi times x over a. And remember, this is only for 0 is less than or equal to x is less than or equal to a, and where n is obviously not equal to 0, because if n is equal to 0, then psi is equal to 0 all the time, and then you wouldn't have the particle anywhere at all. So n actually has to be 1, 2, or 3. Or 4 or 5, etc. Okay, so now we're going to find energy. So we have 2me over h bar squared times a squared is equal to n squared pi squared. We're going to solve for E, which is energy. So E is equal to n squared h bar squared pi squared over 2ma squared. Now remember, h bar is defined as h over 2 pi. So we get h bar squared is equal to h squared over 4 pi squared. So we get E is equal to n squared h squared over 4 pi squared times pi squared over 2ma squared. Simplify, we get E is equal to n squared h squared over 8ma squared. So that's the formula for energy of a particle in a box. And it works whether n is equal to 1, 2, 3, 4, etc. But it has to be an integer, all the way to infinity. So we get E is proportional to n squared. So you'll notice these energy quantities you can have, they're not evenly spaced. But this does show that energy is quantized, just like before. So we get psi, let's start at the bottom here. So psi at level 1, energy 1, we get h squared over 8ma squared. That's your ground state, because it's your lowest state. And then above that we have psi 2, which is 4h squared over 8ma squared equals E2. And then psi 3, we get 9h squared over 8ma squared. That's energy level 3. or psi 4, we get 16h squared over 8ma squared. That's energy level 4. This also shows that the energy of the ground state is not 0. So when we say 0 point energy, that means energy level 1. You also notice that no two states have the same energy. We say it has no degeneracy as a result of the boundary conditions. So remember, energy is kinetic energy plus potential energy. Now we said potential energy, actually we're using V for potential energy before. But anyway, PE is equal to 0 when you're inside the box. Kinetic energy is just 1/2 mv squared, which is greater than or equal to 0. Now if n equals 0, then Vx squared is equal to 0. Then momentum in x is equal to mvx, so therefore the momentum in x is equal to 0. Now we also have the change in velocity in x times the change in momentum in x is equal to Planck's, h. That's Planck's constant, right? So we get the change in x is equal to h over 0. That would be infinity. So the change in x got to be less than a. So delta x can't be infinity. Therefore, n can't be 0 because it would escape the box and all sorts of weird stuff. So anyway, classically, though, we could say energy is greater than or equal to 0 and less than or equal to infinity. But quantum mechanically, E1 is equal to h squared over 8ma squared. So energy level 1 is not equal to 0, and that's 0 point energy. Okay, so let's talk about n is equal to 1, the ground state. So here's psi of 1. So here's from 0 to a. Here's the shape. It's half of a sine function. Now this wave function is real. Now, psi squared looks like this. Notice the highest probability of finding the particle is right in the middle at a over 2. And there are no nodes except for the endpoints. Now for n is equal to 2, see we go from 0 to a. It's a whole sine wave. We have a node at the center. And at the node, the wave function goes to 0. And then for psi squared, we get a peak here at a over 4, and another peak here at 3a over 4, and then there's a node at a over 2. And then likewise for a over 3, or for n equals 3, here's our function psi 3, goes 0 to a. Notice you have 2 nodes. And then notice psi of energy level 3 squared. We have 2 nodes here, one at a over 3 and one at 2a over 3. So it keeps on going. If you have n equals 7, then here's what psi squared would look like for n equals 7. Notice you have 6 nodes. Notice psi squared, of course, is always positive. But then what happens if you go towards infinity? You effectively have a straight line. There are no nodes. So as n approaches infinity, the probability becomes uniform everywhere. So by classical mechanics, you should be able to find the particle anywhere in the box, and you expect it to have equal probability anywhere in the box. So as n approaches infinity, it behaves like classical mechanics. So here's more comparison of classical versus quantum mechanics. Again, for classic, energy is 0 to infinity. Quantum mechanically, energy is only certain quanta, certain amounts. Classically, you have speed is greater than or equal to 0, less than or equal to infinity. Quantum, you can only have... Oh, that's funny, they wrote it energy versus speed. But again, you have energy of n squared, h squared over 8ma squared. So you can use that to find the speed if you know the mass of the particle. And then, of course, classically, energy is continuous. Quantum mechanically, energy is quantized. And then classically, the ground state energy is equal to 0. Quantum mechanically, the ground state energy is equal to h squared over 8ma squared. So what is the value of a? Well, we find a by normalizing psi, which is the wave function. So we have the integral from negative infinity to infinity of psi squared dx. That's got to be equal to 1. So what we've done is shown the probability of finding the particle anywhere is equal to 1, which basically means 100%. It means certain, right? So we're going to split this into the intervals, regions. So we have region 1, 2, and 3, same diagram as before. So we have the integral from minus infinity to 0 of psi squared with respect to x. That's region 1. That's equal to 0 because we can't find the particle out there. And then in region 2, we have the integral from 0 to a of psi squared with respect to x. And then we're going to have the integral from a to infinity of psi squared with respect to x. That's region 3, and that's also equal to 0 because you can't find the particle on the outside of the box. All of that's equal to 1 though. So we get the integral from 0 to a of this whole absolute value, a sine n pi x over a squared dx. Remember, a is constant. So we get a squared is it's the integral from 0 to a of sine squared of n pi over a x with respect to x. Now to evaluate that, you'll have to use a table of integrals. So I think there's one in the back of the book. So we're going to say that c is equal to n pi over a using your table of integrals. So we have the integral of sine squared cx with respect to x. That's equal to x over 2 minus 1 over 4c sine 2cx. So we substitute that all back in. We get a squared times the integral from 0 to a of sine squared n pi over a x with respect to x. That's equal to a squared times this whole quantity, x over 2 minus this whole quantity, a over 4 n pi sine 2n pi x over a, evaluated from 0 to a. And that's going to be equal to a squared times a over 2 minus 0 minus a over 4 n pi sine 2 n pi minus 0, since c is an integer. And of course that's equal to 1. So 1 is equal to a squared a over 2. So we end up with a is equal to 2 over a, the square root of 2 over a. So this capital A is our constant, and this a, remember, is the right boundary of the box. So now we have psi is equal to 2 over a times the square root of 2 over a times sine of n pi x over a. Now remember, we said we don't need the plus or minus because it'll give the same solution. And a is what we call a normalization constant. So look at the handout on orthogonality. So a and b in vectors, well, if they're perpendicular. So if a and b, if they're perpendicular, then a dot b is going to be a times b times cosine theta. A, b cosine 90 degrees is equal to 0. So if the dot product of two vectors is 0, they're orthogonal. The same thing is true with functions. So let's say we have orthogonal functions, then the products of those two functions are always 0. So let's say we have two functions, psi I and psi j. If psi I and psi j are orthogonal, then the integral over all space, the integral of psi I star psi j d tau is equal to 0. Now star means complex, so it actually means the complex conjugate. So it's actually the complex conjugate of I, psi of I, times psi of j with respect to tau. And tau means all space, so this is actually three-dimensional. So for a particle in a box, wave function is not complex, so we don't need the star. As long as they're different states, they're orthogonal. So we get psi I is equal to 2a, the square root of 2 over a, times sine of ni pi x over a, and psi j is equal to the square root of 2 over a times sine nj pi x over a. So if you multiply them together and take the integral to get 0, that you can verify that they're orthogonal.